Thanks everyone for coming. I know why you guys are really here, but it's all right. You have to sit through our presentation, which hopefully you'll get something out of it. So we launched PS4 probably less than 2 years ago, and we've done a lot of work with Cassandra. We've probably made every mistake in the book, and we've learned from it. We've been able to scale and really handle crazy amounts of traffic, and really have learned a lot. We want to share what we've learned with you all, especially in this past year.
So and also, you will get this really beautiful, I really like it, as raffle ticket. So keep it with you until presentation ends, and if you want, just continue keeping it afterwards, just like art. And so there are numbers, and we'll just at the end we'll try to pick a winner by generating random number. So I think it will be fun. And then be careful, by the way, with this thing. I spent 2 hours yesterday stamping it manually, and I'm not really good stamper. I did several major mistakes, so this thing is really, really like fragile. But
yeah, so just be careful with it.
Yeah, but the front side is really cool.
Okay, so go ahead.
So why do you want to listen to us? Actually, slide. That's why people put the slides, right? So I'm Alex. I'm principal software engineer with Sony Network Entertainment. Here's my PlayStation Network ID, laser toys. So you guys feel free to add me as a friend, because we added functionality that allows you to add me as a friend and find me in a PSN, and we'll talk about it later.
And I'm Dustin. I'm also principal software engineer at Sony Network Entertainment. As you can see, I did not put my PSN name. I'm a very private gamer, but you could probably find me through his account. So you can test our features for us. We'd really appreciate it. So moving on. So like I was saying, the PS4 has really, really risen in popularity. It was one of the most fastest growing consoles ever. And just kind of give you a feel for what the kind of user base PlayStation Network deals with. We deal with over 65 million active users. And on record, we have several 100 million users. So you can imagine the amount of interactions that happen, the amount of user-level content that we have to store in our Cassandra. It's quite a large task. And when you think about what PlayStation Network is, you got to start thinking outside of PS4 and PS3. We're very much a multi-platform set of services that provide a broad set of experiences on like PS4s, PS3, Vita, phones, and even televisions that are not Sony. So Samsung TV, we have some experiences on there, and we're continuing to expand and innovate in that direction. So like I said, PS4s continue to sell. And if you look at some of the numbers here, when we launched in 2013, we launched immediately with 2 million consoles. And I don't know if who's worked with like a lot of scale before, or anything that was a startup that got really popular really fast. Just imagine having 2 million users logging into your services over like midnight, immediately seeing that traffic spike was quite an interesting challenge. And as you can see, our growth has just been going on continuously. We're over 20 million consoles right now. We've grown to 10 times the amount that we started with. And in here, one thing you don't see are just the traffic spikes. So this is only PS4 sold. We also deal with traffic spikes when we launch games like Destiny here, or Call of Duty, even indie games such as Rocket League. We're always vigilant. We always have to be able to manage our data in a very good way. So.
Yes, that is a very sensitive topic. We have a really big competitor, and then there are a lot of very smart people working for Microsoft, but it's very hard to compete with Microsoft, a lot of bright engineers. But we was able actually to do really well. And to give you an idea how bad is the competition, how tough it is, you can see it even here today, right? We have Microsoft presentation, us, and Microsoft again. We're like surrounded, guys.
So we're glad you're here to help us out.
Yeah, to find them. But there is one thing, right? Here you go. That's what you see if you go to stores, even today. That's available PlayStations, and here's number of available PlayStation 1s. Yeah, I actually had really hard times finding this one for you.
Yeah, we really struggled to find one available.
Yeah, but so what does it mean for us? It means that we need to iterate fast, we need to bring new features, and also want to make sure that our services are up and running, and then they can scale, and then our backend doesn't fall apart every month or every year. Actually, we don't want to see any outages, right? We want zero impact. We want good latencies, we want really great customer or user gamers experience, actually.
Okay, so what we develop, I mean, if you think about all the functionality that we provide, I mean, it's not just saying, okay, we have a PS4, here's some services inside the PS4, and also off PS4, there's quite a bit of experiences. For example, we actually have a very large social network. Like I mentioned before, we have over 100 million users, over 65 million active users. So you can imagine a social network of that scale. We keep track of all the user activities, what they do, what they play, what their friends are. We have a pretty rich social graph at Sony. We also do things like maintaining your game and video libraries and being able to search through those libraries. And Cassandra is actually a part of that search solution, which Alex will talk about shortly. We do authentication. We have some new features like communities that's coming out. We have parts that power the store. We use it for just some general purpose stuff like caching, and there's a lot more. So if you look, I mean, we have a whole suite of products that we provide. Some are very innovative. For example, we are one of the first to do live streaming TV over IP. So we have the PlayStation View product, which is extremely innovative. We're always on the cutting edge. We have game streaming. We have assortment of products. We've partnered with Spotify for our music business. And as you see, I mean, there's a lot of use cases we have to handle. What kind of backend do we need to support all those use cases? And what we found is that when we tried to make the tough decision a couple years ago, what database solution can provide us with scalability, low latency, and also be able to have us provide for all these user experiences, law debates, a lot of fights, a lot of technologies that we looked over, and Cassandra was the winner. And I look back at those meetings and those discussions, and I'm pretty happy with the decision. So just kind of give you an idea. If you look at all these experiences on the PS4, Cassandra's in there. It may not be obvious, but it's actually in so many of the experiences on the PlayStation. And this is just PlayStation 4. We're not including all other platforms which also use that. So, I mean, when we serve live traffic, I mean, what are we talking about? So our Cassandra clusters are based around serving the end user. The analytics portion, we're not talking about analytics data in here, but we're talking about live to the customer. So we have a bunch of clusters. We have nodes, clusters that range between very simple 4 node to over 100 node clusters. We're streaming tens of gigs of data per second. And we have hundreds of terabytes of just raw data that gets served. And it's just a massive amount of data. And what we have here is just some general read and write numbers. Is that we're dealing with a lot of reads, a lot of writes. We're also transferring a lot of data in these. So that's kind of where those numbers are coming from. So.
All right, so let's now talk about real stuff, right? Advertising part is over, guys.
Yeah.
So watch this. So friends search. So what is that actually? It's personalized search. We had several use cases when we needed ability, like for example for PSN user, right? I want to be able to find my friend of mine on a platform. I want to be able to search by name. I want to be able to search by online ID. And if you think about it, just general search, like how many users are there on this planet? Like 7 billion possible gamers. So you can just, I mean, the solution is pretty obvious. You just put everything in Solar and then scale it up, and then you will be able to search it. But we had several interesting requirements. For example, we want to be able to show your friends on top of your friends of friends, right, and on top of everyone else. And then we want to be able to search inside your friends and inside your friend of friends. So there are another use cases, right? For example, you own a game, and then you own multiple games probably, and then you own multiple videos. And we need a platform that can be very, very fast in answering questions like, how many games do I own? How many PlayStation 4 games? Give me all PlayStation 4 games with, and give me all the pre-ordered PlayStation 4 games. And then it can go and on and on and on and on and on. So Solar is not really good solution, let's say, to handle such use cases. So we had to build something else. So I won't be talking about friends use case here only. So we have PlayStation 4, we have Cassandra. The problem is, you probably notice there's this big empty area, and then there will be one error just going down. No, it will not be. So the first problem that we needed to solve is how do we get the social graph? Social graph can be very, very, very big. It could be billions of billions of billions of edges. It cannot fit in one box memory. It should be distributed. You probably want to be able to access it really fast in parallel. So the obvious solution was to build a microservice on top of it, and then Cassandra was like a good choice to store this data. The problem with it is there are several problems. So the first problem, you can have those power users with a lot of friends, and then how do you store it? Quick question, how many of you use SQL? Right, Thrift.
Yeah. All right.
All right, so if you use SQL, you probably know that there's this partition thing which lives on one node, and then with Thrift, to me it's easy, just one row, it lives on the same box, on the same node, and can be replicated. But if you keep adding, if you model it as a account ID and bunch of friends, then this thing gets really big, and then loading it in memory all the time can be expensive, and it will be slow. And also, people create new connections. People break connections, so a lot of updates going into the thing, a lot of tombstones. We had very interesting challenges. So we decided at the end that let's just build another service on top of it. Let's cache everything locally. Let's have a way to evict the cache. And memory is faster. Unfortunately, unfortunate truth is memory is much, much faster than go over the network. So if data is local, the access is just blazingly fast. You can probably go through all this graph in a matter of seconds rather than hours if you're trying to load it from a database. So next thing, real-time indexer. Why did we need it? So when you search for something inside your friends, like for example, you want to find someone who is friend of your friend by name and sort it and do all this stuff. If you store those personalized indices somewhere, and we tried it, we failed, actually, you will notice very soon that the data size grows exponentially. It grows very fast, and it puts a lot of pressure on Cassandra. Compactions are brutal. CPU goes to 100% when like power user friends, power user. So that's why we thought like, well, maybe we can do a real-time indexing. When a request comes, we'll just do indexing. We have these layers that can give us all the graph really fast, or pieces of the graph, partitions, let's say, and then we'll just index it in real time. And then there are good technologies to do it, like Lucene, for example, right? Very good one used inside Solar, and then Elasticsearch uses it. We can do it. We can do same for sure. And then last piece, actually, you don't want to be indexing every time, right? Because indexing is CPU intensive. So here it goes, like last piece of the puzzle. In-memory personal index. It's a cache, distributed cache. It keeps like user sessions, let's say, for some time. So when you go to the platform, you search, we're not rebuilding indices. How fast is this thing? And then how many accounts, let's say, we're processing? So we're processing millions of accounts per second. That's the number of accounts that is added to index. And then search latency is less than 1 millisecond on average after index is built. So we learned several good lessons, and we found several bugs. So if you use Astyanax, actually, and then as I saw, a lot of people don't use Astyanax, but it doesn't mean that SQL might not have similar issue, right? So in Astyanax, you can specify a number of connections per node, which your application will try to open, and then there is an issue with it. The number of connections always grows. There's no mechanism to reduce the pool. When load spikes, the server will open as many connections as possible. Load goes away, connections are open. And then it's inside Thrift implementation, they're like buffers. Buffers always grow, they never shrink. So when we try to store indices, indices can be big. So what we saw, spike comes, a lot of connections are open, then connections are circling, they're going like this. And then sooner or later, there will be a huge payload that will be either fetched or written through the connection. Buffer gets bigger and bigger and bigger, and application just leaks memory. So there's a fix for it, is just evict connections, right? Actually watch them, and if they're growing too big, and then if you see that there are too many idle connections, just kill them, and maybe kill connections every several minutes, for example, to make sure buffers are there are no leaks in buffers. So another one might apply to CQL as well. So when you want to fetch friends of friends, right? If you store it as account ID friends, the first query will be give me all the friends of myself, right? The second query will be give me all the friends of my friends, right? It feels like a range query when you do a row slicing. So default implementation in Astyanax goes like this. Even if you use token of error, it will go to a random node, actually. If you go to their code, the way they do it, right, when they're trying to find a node that's responsible for a range of a key, it just returns null. Very easy implementation, right? And then it picks random coordinator, and then coordinator does all this magic, and then it goes back. Is it optimal? Not really. You have network hop. So let's go to this slide. And then the improvement actually will be to do something like this, right? You know token ranges, so you can technically find all the right coordinators in your ring because you know ring topology. Astyanax gives you this information, and then you can actually do a query. You query these nodes directly. So it will be one network hop less, hopefully, because Cassandra has this one interesting mechanism to redistribute in the load. And then I'll go back to a previous slide. That's another idea. So as I said, row can grow, or partition can grow. So what we found that you can actually, right, Cassandra uses this multiple tokens and then distributes load by saying, oh, this ID actually falls into this token range. You can do it yourself as well inside Cassandra. And that's what we did for several big rows. We just was splitting them in multiple buckets based on column names, for example, based on identifiers here. And the problem with it, you'll need to do more reads to fetch everything when you do a scan. With Thrift, CQL can do probably sequential scan, but with Thrift you'll need to do at least like n reads to fetch like all these rows. So, but writing is fast, and then you won't blow up your memory when your row is extremely huge. Because our worst case scenario, for example, friend account who knows everyone on a PlayStation, it will be like a really, really big row. Like, all right, and then I'll skip this one. So row caching seems like a good idea. I mean, why not utilize memory? The memory, when stuff in memory, it's very fast. Like Redis is fast, Memcache is fast, and we thought it could be a good idea actually to use it. So we tried it, and it was painful, honestly. Didn't go really well, even though we thought we had a really good use case for it. So we had this GC hell situation. It wasn't like complete GC hell, but after a day of running, instances was going into weird GC mode when there was this firing GCs one after another. CPU was going up, latency was going to hell. It wasn't like that bad. Latency was going up from, let's say, 2 milliseconds to 25 milliseconds, but because everything was kind of optimized for like 2 to 5 millisecond latency, that wasn't really good. So our latency, our customer-facing latency was going up. Yes, it takes longer to restart, actually. If you configure it to store stuff on disk, and then if you restart the bounds node, node takes time to reread all the caches. And then we just decided that, yeah, there are better ways to spend memory, actually, than to use it, to use raw caching. Spark. Yeah, we had this. So there is a Cassandra issue. The problem is, so what we thought we can use Spark to run analytics on top of our production data. We thought, oh, maybe we can have a second DC only for analytics and then stream data in real time, and then we'll run Spark on top of this different Cassandra. We ran some tests, we didn't really like it. So right now we use Spark. We use Spark with Cassandra. We use Spark to monitor Cassandra, right? We use Spark to process all these metrics, and then actually all those metrics go into our logins infrastructure, so we can see what's going on, what is failing, why it's failing.
Okay, so I want to talk about a separate kind of handling of use cases, which is designing for migration. And what do I mean by that? Well, I want to say that change is inevitable. I mean, we launched, a little under 2 years, but the user base has grown. A lot of new features have been added. And things don't necessarily scale as you initially thought. So a column family that exists in a key space may have grown more than you thought. Or different paths, different sets of clusters may have more traffic than you anticipated when you first designed everything. And the thing is, because we have so many interactions, we have interactions between users, interactions between games, users interacting with different features at different times, game launches, totally new things happening. All the time. So what does this do? It may cause more load on different aspects of your cluster. So what really is the strategy here? And how did we handle it? And I think people who've done data migration probably have done very similar things. But I think when you're dealing with massive amounts of data, it's very crucial to know what your strategy is and how to make sure you don't affect the end user. So what we have is a sense of load variation. So let's say you have an application that handles multiple use cases. Okay, so makes sense. These use cases kind of fit under this feature. It makes sense to put in this application. And okay, well, this feature should have its own Cassandra cluster because that's what we should do, have a cluster per feature and manage different use cases. Well, which is good. But then what happens is that, well, sometimes you'll have like unknown or unexpected ways of traffic coming in, and basically just kind of bloats some load into a particular user journey, user flow. And what happens is there's an impact on the cluster, right? You may have some column families that may be a little too wide, and it's basically affecting other use cases, other flows inside the user experience. And what's even suckier is if there's a critical path into one of those other use cases. You're really compromising that flow. So there's a need to change. So we've had situations like this where it's like, okay, we reached this point where our cluster, its use is kind of imbalanced. We need to do something about it. So what do? We do migration. What that means is that we take that aspect, that use case, and move it out, move its data out, move its backend out so that we can scale that one independently and not affect the other use cases uptime. So what do? We basically create a second cluster. They're not connected. They're actually very independent. We create a second cluster, and then what we do is we restore from backups. So we did consistent backups, and we restore it using SS table loader. And also from the application point of view, we're doing double writes and double reads while this is happening. It is a little more expensive, but when you're trying to move a large amount of data and make sure that the end user is not affected and that you want to keep uptime, you don't want to have any maintenance, you got to do this kind of in-place approach. So what do? We write twice. And also we read twice. So what we'll do, we'll read from the new cluster first. If it's not there, we look at the old cluster and then fix the mismatch. So what does that mean? We need to always check for that integrity. And what's key is that we always have to monitor. So every time we have a miss, we keep track of it in our graphs into our metrics, and we keep an eye on it to see how off are these two clusters. And of course, that doesn't solve all use cases. So what we also do is that we have integrity scripts. things where we can iterate and just through both the clusters and just validate and see how far apart they are. And the idea is that over time, these clusters should eventually become very consistent with each other. And then over time, what we do is when we see it's OK, we cut the cord. And now the application is a lot happier. The database is a lot happier. And in general, we're in a good spot with moving our data around. And I think the key point to take away from this is when you're dealing with a lot of data. So some of our nodes have over 500 gigs per node. Managing this and just putting new DCs means transferring so much data, and it pretty much kills your live cluster network I/O. OK, so moving on to the how we can take this a little bit further. Because obviously in that previous one, you're still bound by certain the application itself. So here we're doing the same thing. The main point is that you want to totally isolate that user flow. So we do the same thing, restore from backup, do the fun read write twice, we isolate it. But then you know what, we can also even do this. We can even isolate this out into its own application and keep it completely separate and spin it off to another microservice. Because in some cases, when you first initially looked at a feature, you may have thought that is everything it should happen, but sometimes it doesn't happen that way. Use cases change. So when I say design for migration, there's some things that we do to kind of evaluate and how we can design our features and applications to account for this potential scenario. So what you want to do is really anticipate these critical areas in your feature and basically push into a separate key space. When you put it into a separate key space, it's so much easier to restore backup, so much easier to set up a second DC if you have to, so much easier to move the data around. If it's in a column family, it gets a lot harder. Okay? So some critical areas is if you have any different kinds of security requirements around your data. If it has potentially some kind of user information that may be potentially something you don't want to share with the other column families, well, segment it out. If you have anything that's unbound or potentially could be a lot of large data, if you can have something that creates a lot of edges, you should probably separate this out into its own area. And if there's dependency from a lot of different services to this particular set of data, put it in a spot where you can potentially create new clusters if need be and just separate out the data. So, and for our applications, we always separate our connection pools for each critical section. From the application point of view, it makes it a lot easier to make updates and split it out into separate applications if we have to. And most of all, is just monitor everything. Always monitor the load on the different key spaces, on the different column families. And also, before I was mentioning that you want to monitor when you're doing this migration itself and make sure that your consistency is in a good state.
All right, my favorite section, issues. So everyone that probably in this room attended multiple sessions yesterday, and you know that Cassandra is rock solid, bulletproof, no bugs, no issues. You cannot bring the thing down. It's not possible, period. Well, you can. And I think, yeah, some of you guys probably attended presentations about PagerDuty, like their experiences with Cassandra. So Cassandra is a really good database. It does those things really good, but sometimes there are issues with it. And then this is like probably most important link to remember, right? Issues.apache.org, Jira. So you'll be able to see what's going on with community, what is it talking about, what new features coming. Also, you'll be able to know what is deployed in production right now, because if you're gonna get a call on Friday night, you might not be in the best condition to do a troubleshooting and figure it out by yourself. So it might be better to at least know ahead of time that, well, we deployed version 5 and there are all these open issues actually. So we might phase them in production. And then when new version comes, right, is released, it's easier to think about, so if we upgrade, what we're getting from the upgrade. And that's why actually if you run in multiple versions of Cassandra's in your production, it makes it very, very hard to track all those changes, because now you need to know, like, oh, we have version 2.0.15, 14, 13, 1.2, and then it just hard. So upgrades are a good idea. Actually, you don't probably want to run 2 years old Cassandra clusters. At least if you're running, you should know what is going on with them. What are the possible issues inside? Yeah, that's my favorite one. So Cassandra, 2 rings, right? They should not connect if you don't want them to connect. And then also, when you have 2 rings, right, if you set it up as one DC, second DC, they will be communicating. But in this example, you see this confused node in between. What happened? We had one cluster, we had second cluster. Then at some point, this node was decommissioned. It crashed, it died, we removed it. Then later, and then those clusters are using vNodes. Later, we brought it up again, but it's all elastic. We do use Amazon, all those EC2 instances. So we just assign it to another cluster, and then we saw it as everything okay until we saw that first cluster still thinks that node belongs to it, and then first cluster was showing it as down, second cluster was showing it as an up, and we thought, well, okay, at least Cassandra is not streaming data, and then everything should be fine. We were planning to actually deal with it, and then I was running. I was running a sequential scan to prepare data for Spark analysis later, and I found that when I query this cluster, that first cluster, some nodes respond with key space is not found. And like, well, how is it possible? It's definitely there. And then I started digging, and I found that our client library wasn't aware that node is down, because from client point of view, it calls through indescribe, it gets all the nodes are fine, so it thinks, oh, this one belongs to that cluster, it queries it, latency is okay, so it was actually going to this cluster. And then we didn't have any data loss, because actually the first one wasn't really mission critical, but I was really surprised that it's possible actually, but we saw it. Second problem that we saw, that's a puzzle, so help me with it. So at some point at time X, we saw a spike and load averages across all our Cassandra instances, right? Looks like a lot of users just were downloading a new game like Destiny or something. TCP connections from the applications to the nodes spiked. So you probably see that thing, right? That means that we had the clusters that we were ready to decommission. We streamed data, it was just there, we were ready to decommission it, it was just hanging around. So definitely like a spike of connections, spike of new users rushing, probably some new service was released, like some new maybe feature. But guess what, network out across all the nodes dived, like there was a spike and then it went down. Any ideas what happened? Any guesses? Oh, no, but it was a good one. Anyone?
Anybody see this before? Anybody experience?
No. No.
Very close.
Very close.
Was it really compaction? Maybe.
And we did it before. Yeah, but not that. No, not that time. All right, so that's interesting. It's another issue. Memory meter. So it's a thing that monitors how much memory is available for the instance, for Java, so to know when to start flushing mem tables, and apparently there's an issue with it. So what happened? Amazon killed our node, and we had to decommission it. We restarted it, we decommissioned it, and then it streamed data to other nodes, and then the streaming part can trigger it. Memory meter goes into an endless loop. It consumes 100% of CPU. Cassandra nodes actually die, and they cannot process data. They become really, really slow. And we were using vNodes, which made the issue even worse, because here, right, node just streamed to 2 of them. With vNodes, what happened, it's just blasted. It just sent data to all of our Cassandra nodes. So a lot of them went into this hell. The solution, DataStax engineer helped us a lot with it, and the solution was to just do a rolling restart until issue goes away, and then just do an upgrade to the latest DataStax version, because we use DataStax. So That's why I said you want to know what's deployed. Another one, interesting. Last time we were using 2 disks. When we presented last year, we said we went through RAID 0, RAID 1, and then we ended up using 2 disks. We thought it's a good idea. It's not. There are 2 problems with it. First compaction starts. Red one is data, so blue one is empty space. This one is used space. First compaction compacts to disk 2. Then there are writes coming. Cassandra can start another compaction. It's not scheduling it really well. And then at some point, disk is full. So the current behavior is node will just go down. But at that point, we were running a version that was doing interesting thing. Node was actually decommissioning itself. Node said, fine, I'm done here. Sorry, can't handle it anymore. Stream data to other nodes, and then just left. And we were like, well, I thought I have 20 nodes in this cluster. Why it's only like 19 and then like 18? What is going on here? It's fixed now. Default behavior is just stop. Yeah, so that's actually, yeah, EBSs, that's what was going on. Disk health checker Java, removing this node from the RIN for the disk is close to full. Very nice message. Yeah, EBS, that's what we were doing to save other nodes. We were just adding EBS volumes so they can at least handle all these compactions, and then we had to remove them. Very interesting. Thank you thanks to our ops guys for making it happen and keeping stuff running. And that's actually it. That's it.
That is all.
Yeah.
Okay. So, all right. So, okay. We can take questions. Or?
Yeah. So, well, right now it's like Q&A plus raffle, and I believe we don't have this hard limit because no one's coming to this room. It's a lunchtime actually, so we have some time.
Thank you.
Yeah.
You asked that guy.
That's how I do it.
Okay. So, if there's any questions, yes. Or should we? Is there like a microphone we can? So,
I had a question about your trick. So it looked like what you did was basically took the account, appended an underscore and a number to it. And I was curious if you did it that way, if you considered adding another column for that bucket, and then basically making the partition key, the 2 of them combined. It seems like it would do the same thing.
Like a composite key type of thing.
Yeah.
Yeah, I mean, that's also a possibility as well.
I was just curious.
No. I think, conceptually, that's
okay.
what it is.
Okay.
Yeah.
I didn't know if there was a performance reason or something that you would only use one column.
To do
the underscore thing, the composite key thing that you're doing.
Oh, but composite key is it's still same problem.
Yeah.
Well, if you make it both of those part of the partition key, right, the 2 columns together, then it should still partition it separately anyways, right?
Good question. How will it be stored in Cassandra? And how it will be retrieved if you do this with if you put 2 things into partition key?
So when your partition key would be the 2 columns together, right?
2 columns or 2 rows. So our problem was we use Thrift.
Yeah.
CKL right now, internally it is Thrift, right?
Yeah.
So you have your row key, right, or partition key.
Yep.
Actually, it can be composite, but if it behind the scene it's just a bigger key, then it doesn't matter what you do. But yeah, technically you could,
I was just curious for maintainability reasons or if there was performance trade-offs either way with that. So, okay.
How long did it take you to perform your migration in those scenarios?
Okay, so the migration took a lot of it was in planning, and a lot of it was in testing. But it took, Fred, how long was it? It was like actual execution was probably within a week's time, and then just data validation, we let it run for like a couple weeks till we saw that the difference in the data was not there. So when we felt comfortable and said from a business perspective, this just looked good, then that's when we cut it. So the migration is just an ongoing thing that was kind of left on for a while.
I have another question too.
Yeah.
In regards to using EBS, how did you handle that at the performance level?
So the thing is, we were using EBS primarily to offload these large compactions. I don't know who uses what kind of compaction strategy here, if you use size tiered or level tiered or whatever, but no, if you don't have that 50% of space, sometimes you'll get the situation. You don't want to get that situation, but if you do get in that situation, you need somewhere for it to compact, right? So we throw the EBS on there, let it compact, and at least in our case, what we've had is that data is being deleted. It's not really being cleaned up. So when we put on the EBS, we should get something less back out, and then we just remove the EBS. So there is a performance hit, but our use for it is primarily in the compaction realm, is what we're really focusing on, and it gets us out of this the really bad situation that we're in. Otherwise, what happens is that the disk fills up. We had the problem where the nodes would just kill themselves. They couldn't handle it. So it was a way to kind of save the cluster.
And is that permanent, or did you automate that?
This is, well, actually, it was some manual work, and then there's some automation in terms of like spinning up new nodes to kind of fill in those gaps sometimes. But yeah, it was a lot of babysitting, I'd say. Yeah. Some good code there.
I can help you now.
People can
I'm
code
ready.
review, please.
I give it a good code review. Yeah, so the migration strategy you talked
Yeah,
about sounds
yeah.
pretty similar with how we've been thinking about it. One kind of unanswered question was how we might deal with multi-region replication there, because like you can do double writes in the same region. That that
yeah.
seems great, but as soon as you have another region multi-master that's replicating it seems more
Yeah,
complicated.
we've had situations where we did multi-data center, and one of the big killers was this network. So, for example, we had a data center. We have a data center in Japan, and transferring data along the wire, when you get a lot amount of data, you will never catch up. You'll just gather hints, for example, or you'll just do stuff. So some of the mechanisms you always do is queue up, and then use the queue to do it. Then you still need ways to validate the data, because you'll never, with the amount of writes coming in, you'll never be able to be 100% confident that the data is exactly the same. And the way we're approaching migrations, we don't necessarily use the data center connection, and we don't run repairs like that, because the amount of data we have, we don't want to take down our live cluster. So yeah, you can use a queuing mechanism.
Cool, thanks.
And to give you just an idea, so when we last time talked to Amazon folks from DynamoDB, actually they were planning to do a cross-region replication using messaging mechanism. Actually, they were thinking implementing it using their simple messaging service, but
Yeah.
just
Yeah.
In the search use case, you mentioned that the Solar was probably not a good fit for you, and because it was a graph
Yeah.
kind of thing. So just curious to know, like, did you guys try out with Titan or any other graph database?
Oh yeah, so I think initially we went through actually a lot of graph databases. We would tried Orient, we tried looked into Neo4j and stuff like that. So for our particular use case, the thing is we wanted to go for a very personalized search. So the main difference is that we wanted both. We were very greedy. We wanted personalized search. We also wanted global search. Right? We wanted to be able to search across all PSN users, or I wanted to search within my local graph. I wanted to search within my own library, for example. And the problem is when you have this kind of personalized aspect in a big index, you can imagine how big that grows and the performance hits that you will run into. Your reads take an incredible hit, and you're always re-indexing the entire thing. So I think for us, we moved, for the graph question, we moved out of it because the amount of users we had and the amount of links between users that we had exceeded what the technology that we're looking at could handle. For example, even for J, the time was that whole like master-slave kind of architecture. Without doing any kind of sharding mechanism, it was very difficult to do. So that's why we leaned on this Cassandra distributed approach and then doing the personal index to handle the searching within someone's own social graph. So, yeah.
Let's take one more question, and then we'll get rolling with this thing so that you guys aren't, all fighting each other in the lunch line.
Just a quick question about your migration. So I was curious, what do you guys use to back up your ring, and how long did it take to actually restore from your backup?
Okay.
Maybe I should ask your ops guy.
Yeah, the thing is, the way we back up, we push everything into S3. We do increment. We have actually our own handwritten scripts that will do incremental backups. So we have nodes that have over 500 gigs. We have 700 gig nodes, even things that get close to a terabyte. And you can imagine just trying to back up the entire thing for a 100 node cluster will take forever. So we do incremental back. So backing that up is quite fast. And also restoration, it could take days actually to do that. The idea is that we're not doing any kind of weird replication or anything like that that puts strain on the cluster. We're doing it completely separate. And so we have a little bit of luxury in the time. But so yeah, usually we just take those backups from S3, put them on, and depending on how big that is, that's the data transfer time.
Thank you.
That's it. All right, guys, the moment everyone is waiting for.
All right, let's see.
So it's all fair, right? I imported Scala.
Yeah, just you
random-
proofread it and make sure that he's not doing any weird
Yeah,
seeds or
no
anything.
bugs. Unit tested. Welcome. I can actually put it on GitHub later if you want to reuse it. Like
Open
during
source that.
Yeah, open source completely. We're giving it to community, right? So let's see. Oh wow, like wrong button. So 289. Anyone?
289.
It might be a miss.
We'll give you a.
Yeah, because
give you a few
it was
seconds.
randomly distributed. So
All right, nobody's screaming, so nobody won yet.
nobody, right? Okay, good.
Okay.
Right.
Yeah, if we miss 3 times, we get to keep it. So.
Okay, this one.
468. I heard a grunt. No. Yeah, I think you have to go for lower numbers. I don't know if you handed out that many.
Yeah, but it's a little bit random.
All right. Okay.
1-4. Yeah.
145.
Oh,
Oh, there you go. Third time. Lucky. We're about. Can you take a picture of a? Oh no, he wins and everyone just runs out.